Okay, we're talking about conservation of momentum now. Now, quick review. Momentum, letter P. I don't know, makes no sense. P is equal to m times v, mass times velocity. And of course, that means the units are kilograms times meters over seconds. There's nothing in that that cancels out. There is another unit, though, that is equal to it, and that is a Newton times a second. If you remember back, a Newton is a kilogram times meter squared divided by seconds, not meters squared, it's meters divided by seconds squared. If you multiply that times seconds, you get kilogram times meters divided by seconds. They are the same thing. So therefore, it's important to understand that. Now, key thing, collision, you have to be moving to have momentum. Things that are sitting still have zero momentum. So you want to look for words like rest, stop, things like that. You're then going to know that P is equal to 0. Now, probably the most useful thing that we use momentum in is collisions. When things collide together, we know that momentum must be conserved. So let's take a look at a simple example problem. I have block A, 2 kilograms, and let's say it's moving at 5 meters per second. It's going to hit block B, which is 4 kilograms, and is stationary. Afterwards, block A stops. I want to know what's going to be the speed of block B. So what I'm going to do is I'm going to approach it this way. I'm always going to start with the same basic statement. Momentum before equals momentum after. That's going to be my key thing. Anytime I see a collision, that's one of the things that I want to take. It's an inviolate law. It has to work. So therefore, I'm going to say the momentum of A before plus the momentum of B before equals the momentum of A after plus the momentum of B after. And then we attack it from there. Well, let's put in the terms that are 0. That's 0. And of course, afterwards, A stops, so it's 0. So over here I have MA/VA is equal to MB/VB. And I'm going to use a little prime mark to signify after. So now I plug in my numbers. On this side, I'm going to have 2 kilograms times 5 meters per second. Over here, I have 4 kilograms times VB. Okay, so this is 10. 10 divided by 4 is 2.5 meters per second is equal to VB prime. And that you've answered it. And that also makes sense if you think about it. The speed is going to cut in half because you have a block that has twice the mass. So if it has twice the mass, it's going to have half the speed. Now let's look at one that's a little more complicated. Let's have two things hit together, but now let's have them stick together. Let's do the same ones we just did. 2 kilograms, 5 meters per second, and over here I'm going to have 4 kilograms stationary. Then afterwards they stick together. So what I want to do now is figure out how fast they're moving afterwards. Still start with the same base statement. P before is equal to P after. So I'm going to have MA/VA plus MB/VB is equal to MA/VA after plus MB/VB after. Key thing is that they're sticking together. So I know that these values are going to be the same. So now I'm going to do this. I also know that this term is equal to 0 beforehand, so I can get rid of that. That's the only thing in this case that's going to be 0. So now I need to solve it. 2 kilograms times the speed of A, which is 5 meters per second, gives me 10 units of momentum. That's equal to, well, here's a good thing that I can kind of factor this out, and I can say MA plus MB times the final speed. I don't care what you call it, to be honest with you. I have 10 kilogram times meters divided by seconds over here. My combined masses over here is 6 kilograms times VB prime. So VB prime is equal to 10 divided by 6. That's about 1.67 meters per second, and the math gods are happy. So what you want to do is look for key things that constrains it. They may say one object stops, they may say they stick together, and that will give you some clue in how to do it. In class we will go through how to use a momentum table, which will help you if the problems get more complicated. Key thing also to understand about momentum in general, momentum is a vector quantity, so therefore direction matters, and that will become more apparent as we do some more practice stuff, but the direction matters. It is also conserved in every dimension. Quite often we're going to deal with linear momentum, but it also deals with 2D and 3D momentum, and that's kind of important. Linear is probably the more common case, but if you're playing a game like pool, for example, it's two-dimensional momentum. So we're not going to do numbers with this one right now. We'll do numbers later. But if you have something like the cue ball going into the 2 ball and the 3 ball, that's your initial case. Your initial case, this has all the P. These both have 0 P. Now afterwards, what's going to happen this, I'm going to say the cue ball stops, B is equal to 0, and what's going to happen is the 2 is going to go this way, and the 3 is going to go this way. If I add those two vectors up, remember when you add vectors you go tip to tail, when you add these vectors up you get that. This is, well, let's say this is the momentum of the 2, this is the momentum of the 3. This is my final momentum, P final. And P final equals P initial. They're the same length. So therefore it works. We'll do some more of these in class to give you some more math practice on it. But it works even in 2 dimensions. It even works in 3 dimensions. So more on that later.